Hi, in this video I'm going over a few homework assignment problems from section 4.4, 4.6 and also 4.7. The first question I got asked from the students was the problem 23 from section 4.4. So let's go over this question. So we are given the revenue equation for some farmer, and we are asked how many pounds of fertilizer should be applied per acre to maximize the profits. So in order to find how many pounds, the first thing is we are given the cost, we are given the revenue equations. Now you just need to find the profits because they ask you for the profits. So the first thing you have to find the profits function, and recall that the profits is equal to the revenue minus the cost. So your revenue is here 700, subtract 400, e to the minus x over 100, subtract the cost, and the cost is, we know that the cost is 0.4 per pound. So x is the number of pounds, so 0.4 times x is the cost function. So whatever you get for the revenue, subtract the cost function here, should get you the profits. Now to find the point to maximize the profits, we must first find the critical point of the profits function. And to find the critical point, you have to find the first derivative of that, and then set that equal to 0 and solve for x. So if you take the derivative of the profits function here, p dp over dx, the constant 700 becomes 0. Okay, actually let me do it here so you can see. So let me put here. Okay, so let's do it here. So we got the profits function, p of x equal to 700 minus 400 e to the minus x over 100 and minus 0.4x. If you take b prime, the constant becomes 0, right? And then the exponential function stay the same, right, over 100, and then the constant here, the coefficient here. However, this is not a single x, this is something else, so you have to apply the chain rule by taking the first derivative of that exponents here, and then take the prime, and minus 0.4x, you take the first derivative, that becomes 0.4. Now if you take the prime of this one, it just becomes this is x to the first power, so it just becomes minus 1 over 100. You just take the coefficient here and just carry out all of this, and minus 0.4, and now a minus and a minus, when you multiply that together, that's give you a plus, and 400 divided by 100, that's give you 4, e to the minus x over 100 minus 0.4. So this is your p prime of x, or dp over dx, which is right here, right? And then you just set this one equal to 0 and so for x. So set that equal to 0, then move 0.4 to the right side, then you have that's equal to 0.4, and then you solve for x. So by dividing both sides by 4 from here, right, dividing both sides by 4, you get e to the let me do this here. So e to the minus x over 100 equal to 0.4 over 4. Now you want to take away the negative exponent, so we can do that by changing that to positive exponent, but you have to flip the other fraction here, 4 to the top and 0.4 to the bottom, because you are changing the negative side, and remember the negative is the reciprocal of the fraction. That's why you have to flip 4 and 0.4. So that's why I end up to here. And in order to solve for x, you want to take away the base e, So you can do that by taking the ln of that on both sides. So the ln and the e cancel, you have x over 100. That's equal to, for the ln of 4 divided by 0.4, and just multiply by 100 on both sides. You are solving for x. So x is ln of 4 over 0.4 multiplied by 100, which is this one, or 230.259. So this one is the critical point where the first derivative is 0. Now, in order to know if this one is the max profits, you must first to confirm this one is really the point where you get the maximum or the max profits. So in order to confirm this one is the max or the local max, you can use the second derivative. So from here, from this one here, from p prime, which is this function here, we can then find p double prime, the second derivative, and the constant becomes 0, so we don't care about that. Now 4 stay the same, and then the exponential also stay the same here. And because this is not the x only, so you have to apply by the chain rule, take the prime of that, and also that's become minus 1 over 100, and multiply by 4, that's become minus 4 over 100, and then e to the minus x over 100. So this one is your second derivative, which is here, right here, which they simplify the 4 and 100 to 1 over 25. You know, this one, the exponents of anything is always positive, and we are multiplying by a negative 1 over 25. So this one, the second derivative is always negative for all the value of x. And the second derivative is less than 0. It's concave down, right? It's negative, it's concave down. And you should have the maximum point. Or in this case, we should have a local max. And you can confirm that the critical point we found here, 230.259, will give you the maximum of the profits. So the farmer should apply about 230 pounds of fertilizer per acre to get the maximum profits. And the second question is, what is the maximum profits on a 200-acre farms? Okay, so how do I do this question? Let me pull the solution here. Okay, so to find the profits of so we got the location to get the maximum profits, which is 230. So you just have to take this 230 pounds and then plug this in the profit function, or p of 230.259 in this function here, and then you should end up with a maximum profits. Now that's maximum profits is for 1 acre only. Now you want this maximum profits for on a 200-acre farms. That's why whatever you get the number here, multiply that by 200, or it should be 567.9, and multiply this one by 200. This 567.9 is from here, and then multiply that by 200, and you should end up with this number here, because this one is only for 1 acre only, and you want 200 acre, so multiply by another 200, because this one is dollars per acre, so make sure you multiply by 200 to get to 200-acre farms. Okay, so that's the first question I got asked from the student. The next one is problem 19 of the same section here. So 19 is 4.4. So for this question, we are given the demand equation of a product P equals something. right? This is the price with respect to the Q. Now they want you to write the revenue as a function of Q and find a quantity that's maximize the revenues. Okay, so we are given the price P equals to something. So you want to find the revenue. Remember, the revenue function is the price times the quantity, P times Q. We are given P, which is this one. So just take this one, multiply by Q, do the distribution of Q to here, you get to this function. And then again, to find the maximum of something, you have to find a critical value. And finding the first derivative of that R prime, and you take the first derivative of this one, 27Q become 27, and then bring down 2 to 0.01, that's 0.02, subtract 1 from Q, and equal to 0, and then and so for Q. So you move this to the right side, divide both sides by 0.02, you get Q to be 1350, and it is one the maximum or the mean value. We can use the first derivative test to test for the local max or means. So you are looking for one value on the left of this one, and then you find that R prime is less than 0, and then you're looking for one value on the right of this one. You find that the left of on the left of this number here, you have some positive slope or increasing. On the right side of this number here, you are getting some decreasing value, or the function is decreasing. So we go from increasing to decreasing of a particular point. That means you are reaching to a max value. So you are going up, increasing, and now decreasing. So this one should be the max value. So 1350 should give you the max revenue function here. So we can conclude that the local max should be here. And they ask you for the quantity to maximize the revenue, which is 1350 here. And what should be the price of each item at this production level? So to find that one, you just plug in the quantity Q into the original function P here, and for Q 1350, and that should give you P to be $13.50. And they ask you for the total revenues, which is the P times Q. We know that the price is $13.50 multiplied by Q, which is also 1350. Together you get 18,225. The next question is 24. So we are given again a demand equation for quantity of product of price P. Q is the quantity. The company is producing the product report the cost C. The cost, they also give us the cost function here. Now you want to express company profits in dollar as a function of Q. So to find the profits, remember the profits, we use the notation, the letter pi to be the profits. So the revenue is the P times Q. P is here, Q is just Q. So P is this one, because we want everything in terms of Q, right? As a function of Q. So you want to write P as something with Q, which is this one, and Q is already a Q. So you get this one as the R function, and this is the revenue R, and you subtract R and to the cost function, which is here. Revenue subtract cost give you the profits. So do the subtraction of this polynomial, you should end up with the secondary polynomial here. And to maximize the profit, to maximize this profits, again you have to find the critical numbers by finding the first derivative of this profits function. So bring down 2 become tens, subtract 1 from Q, and then that's become the constant 1997. The constant phi, you take the first derivative, that's become 0, and you set that to become 0, and so for Q, you end up with 199.7, and that is the production level to make the company to get the largest profits. Now, what they ask you next is what is the largest profits. That is what is the actual amount of money with this quantity here. So you have to get Q to be 199.7 and plug that into the profits function, which is this function here. Anytime you see Q, that now become 199.7, and that's so for the money for the largest profits, because we are looking for the profits at the largest point to maximize the profits. So that should give you the largest profits. Okay, let's do the next problem from section 4.6. So 4.6, let's go over question 12 and 15. So I got asked from 2 questions from this section. 4.6. So question 12, 4.6. Okay, this question we are given the demand curve of a product is given by P equal 100 subtract 10Q. P is the price, Q is the quantity. Find the elasticity of demand E when the price is 70, and if this price rises by 2%, find the corresponding percentage change in the demand. Okay, let's quickly go over this question. So we know that the elasticity of demand is given by the formula E equals the absolute value P over Q dQ over dP, or you are taking the first derivative of the function Q with respect to the price. Now, because we are given a function P and Q, so therefore you want to take the derivative function formula here. Now, in this formula, we are taking the derivative of the Q function, dQ, over dP, and we are given dP only. So the first thing is you must solve this given P for Q, because you are taking dQ first. dQ in terms of P. So once you solve for Q, which is 120 minus P over 10, then you can find dQ over dP. And how do I find dQ over dP in this problem? So let me quickly do that here. So when you solve for Q, which is Q is 120 minus P over 10, and we can just split this 120 10 minus P over 10, and Q prime is actually dQ over dP, because Q now is in terms of P, so the constant now becomes 0 when you take the derivative of that, and then this is the first power, so you just get the coefficient, which is minus 1 over 10. So the derivative of the Q function, or the Q over dP, is minus 1 over 10, which you can see is from here. Once you get that, we want to find the elasticity when P is 70. So when P is 70, which is here, when P is 70, then Q is 120 minus 70 divided by 10, or Q should be 5. So you get P, you get Q, you get dQ over dP. So just throw them all in this formula and do the calculation. You should get 1.4. And we know that the elasticity of demand is the percent change in the demand over the percent change in the price, or the ratio between the percent change in the demand over the percent change in the price. And I said that when this price rises by 2%, that means you can find the percentage change in the demand. So you are looking for the percent change in the demand, or you are solving for the numerator percent change in the demand. So multiplying both sides by percent change in the price by E on both sides, you are getting percent change in the demand. And we got E, the elasticity of demand, to be 1 before, and the percent change in the price is now 2%. So 2 times 1.8, so that gives you 2.8%. The reason that we did not convert the 2% to the decimal because the percent change in the price, the demand now is also in the percent units. So you want to keep 2 by 2%. Okay, and the percent change in the demand is 2.8%. And because we know that dq over dp less than 0, the derivative of q over with respect to p is negative, and because this one is negative, this corresponds to 2.8% fall in the demands. Okay, so we are decreasing here, 2% decreasing in the demand, right? Because we get a negative for dq over dp here. Okay, the derivative is the rate of change of the quantity over the price. It is negative. That means as you increase the price, the demand goes down. Okay, next problem for this section is 1.5. Sorry, 15. Okay, the demands is given by this equation. Q is in pounds of yams, and P is the price of the pounds. As the price of $4, what is the total revenues for the farmer? Okay, let's pull out the solution here. Okay, so we know that we are given the quantity, which is 5,000, subtract something, and this is the demand, right? Q. So the quantity, so we know that's at the price of $4, so $4 go to P, so you get Q to be this number. And the revenues, the total revenue is what? Revenue is always the price times the quantity. The quantity is this number, the price is $4, so multiply that, you get $18,080. That's for part A. And then they ask you to write the revenue as a function of price, and then find a price that maximizes the revenues. We know the revenue equation is P times Q. Q is given here, so let's multiply that by P and do the distribution of P to here to there. You get this function R. And to maximize the revenue, you find the derivative of that, which is 5,000. Take 3 times 30, subtract 1 from P, and set that to be 0, and solve for P. We disregard the negative value for P because the price is only something positive. In this case, the negative doesn't make sense, so we only consider the positive case, 7.45. And then you can use the first derivative test to test for 1 point on the left side of this number and 1 point on the right side, and you are going from something positive increasing to something decreasing, so you should get the max, the local max at this price. So so RP has a local max at this one. We also test the function as p equal 0, the price 0, which is the only endpoint. Right? You're looking for the max value, the local max. So you're looking for the price, the revenues when the price is 0 and when the price is at the critical point. We know that's when the price is 0, we don't have any revenue. So you started with 0 money, and now we use the point of the critical point, and we can find the revenue at that point, which is 24,000 something here. So this should be the maximum value, and we can conclude that the revenue is maximized when the price is 7.45 per pound. And now for C, they ask you what quantity is sold at the price you found in part B, and what is the total revenue. So the quantity function is given here. This is here. So the price now, we just take the value we got from 7.45, and you can find Q. Just plug in that P here and find that Q, and then take Q times P would give you the revenue, right? P times Q. And the last one is what is the elasticity of demand when the revenue is maximized. Again, we apply the same equation, P over Q dQ over dP. And dQ over dP, we know Q is this function. So you are taking the first derivative of this one, which is bring down the 2 to here, because this is a constant, becomes 0. So 30 times 2 is minus 60p, and PQ, we know this is the price, this is the Q, so plug them in here. You should end up with around 1. So which agrees with the results that maximum revenue occurs when E is around 1. Okay, that's the end of 4.6. Now let's go to 4.7. There are 4 questions that was asked on 4.7. 4.7 is about the logistic growth model. So the first question I got asked from 4.7 was question 6. Let's see what's that question. 6 is here. Okay. So 6 in the following table shows the total sales in thousands since the new games were brought to the market. Plot the data and then determine the point of dismissing returns, or the inflection point. Okay, so you just want to plot this one, so it's easy. The months on the x-axis, the sales is on the y-axis. 0, 0 is here. For 2 months is here, and then you get 2, which is around here. 5 is here, 10 is here, so 2 is around here. For 4 months, you get 5.2, so it's around here. Just keep doing that and connect the points together. You get to this graph here. The point of dismissing returns, or the inflection point. Okay, so you are looking for the point that the sales is growing fastest. So how do I get that? We know that when the total sale reach roughly 34,100, which is, we can find from here, this is in thousand. So 2 here is 2,000. 5.2 here is 5,200. So this number is in thousand. So if you look back here, from 2 to 5.2, you are increasing by 3.2 the value. And then from 5.2 to 9.3, you take the subtraction 9.3 subtract 5.2, you get 4.1. So you go 3.2 and then 4.1 and 18.9 subtract 9.3, that is 9.6. So you go another 9.6, and then from 18.9 go to 34.1. So take 34.1 subtract 18.9, that is 15.2 to get from 18.9 to 34.1. And then from 34.1 to 44.2, you take 44.2 subtract 34.1, that should give you 10.1. So from here to here you get 15.2, but starting from here to here you get back to 10.1 only. So we are starting to decrease from this point and after this. So we are reaching to the max value around 34.1, but this is in thousand, so it should be 34,100. And we know that this is halfway, so you have to multiply by 2 in order to get to the total sales. Okay, let's do question 10. Okay, so question 10 is saying that let me pull up the solution. A community in Southern California, Mexico, has a variable fixed amount of lands, and this is the proportion P of farming T years after 1935. Now, what proportion, that is, what is the value of P of the land was used in farming in 1935? We know that 1935 is the year this model was using. So at this year, T is after this year. So that means that this year T should be 0. So 1935 means that T equals 0 in this model. And you sub in 0, you find P to be 0.25 or 25%. In the long run, what should be the value of P? So in the long run, that means when T is approaching to a very large number or infinity, and the exponent to a negative value, that means you are getting a very, very large negative value on the exponent. So let's try it here. Okay, so when T is getting very large, you get 1 over 1 plus 3 e to, for example, e to negative infinity. It's very large for T. And e to the negative infinity is equal to 1 over e to infinity. And 1 divided by a very large number, that thing becomes 0. So 0 here times 3, that is 0. So 1 divided by 1 should be around 1. So that is why you get 1 for in the long run. And when was half of the land in use of farming? So to find half of the land, okay. So to find half of the land, that means we can solve this by the graphing here. So you enter the function into the graphing calculator and trace the resulting curve when it hits 0.5. Okay, so 0.5 on the curve happens when it's around 39.9 or 40, right? 0.9. So 40 years after 1935, and 0 is the year of 1935. So 40 years after that is 40 years plus 1935 or 1975. So make sure you graph this one on the graphing calculator or any website of graphing. And then the last one is when is this proportion of lands used for farming increasing most rapidly. That is, we are looking for the point halfway between the total farming, the lands, or the inflection point. And we know that this is when as the point 0.5, and we just found that in part C, which is 1975. The same thing. So basically ask you the same type of question as C and D. The next one is 14, which is here. Okay. So the first thing is you you are getting the curve for the total number of people P infected with a virus. Now they ask you what should be with the time T in weeks. Suppose that 8 people originally have a virus, and that in the early stage of the number of people infected is increasing approximately exponentially with a continuous growth rate of 1.78, and in the long run approximately 4,000 people will become infected. So what would be the value of K and L? K is just the growth rate is 1.78, and L is a limiting capacity, or in the long run what should be the number, and it should be 4,000 people, right? L is just the value in the long run, which is 4,000 people. For B, use the fact that when T equals 0, we have P to be 8, so find C. So we know that L is here, K is here, so we know everything from part A. And now you just plug in the 0 for time T, and you're solving for C. When T equals 0, then this function becomes 8. That's why the whole thing equal to 8, and you are just solving for C. Once you get C, you can now that you have estimated the value of LKC, what is the logistic function you are using to model the data? So we have everything, C, LK, so just plug that in the function and you get the complete P of T function. So you just plug everything together for part C. And then from part D, estimate the length of the time until the rate at which people are becoming infected starts to decrease. So it starts to decrease, or when it's reached the highest point or the inflection point, and from there it starts to decrease. So you are looking for the point of diminishing returns, or the inflection point, and that happens when so we can do this by finding the value. So the total is 4,000, so the inflection point happens is when this one is halfway, or 2,000. So 2,000 is around here, and that's happened when T is around 3.5, right? This is halfway, 3.5 for 2,000. So you can use the graph to estimate that. Okay, so another question is number 15, the last one. Okay, the last one, they ask you to find the exact coordinates of the point at which the following function, the curve, is steepest. That means we are looking for the point is growing fastest of this logistic curve, or the point of inflection, in another words. So to find the point of inflection, you first find the first derivative of this function here, and the whole quantity in the bottom here, you can bring it to the top and make that to be -1, and then take the first derivative of that, which gives you this function here, and then set that to be 0, and so for the critical time t, so which is this function here. So this is just turn back to the problem of finding the critical point and solving for the local max. And yeah, this is be the time t that you can get the max value. Okay, that should be the end of this section, and we can discuss more if you still have questions in the class. And thanks for watching.